Good morning, everyone. My name is Tong, and a second-year PhD student at Zhejiang University. Gaoyi and Dongwei are both my supervisor. Today, I will present SimEnc, a high-performance similarity-preserving encryption approach for deduplication of encrypted Docker images. Encrypted Docker images are becoming increasingly popular in registries for privacy. For example, encrypted images are already widely used in IBM Cloud and AWS Lambda. However, storing a large number of images results in huge storage costs. For example, Docker Hub hosts hundreds of million images, which occupied more than 15 petabytes of storage space in 2020. A recent analysis of the Docker Hub revealed that about 97% of files across different layers are duplicates. It highlights the essential need for duplication to save space. However, duplication for encrypted images is difficult. That is because duplication exploits identical content while encryption makes all contents look random. So as a countermeasure, previous work utilizes the message lock encryption. Specifically, they first decompress each layer in the container images and are broken up into fixed-size chunks. Then the chunks are encrypted by the MLE and are performed with chunk-level deduplication. So the key technique here is MLE. It can generate encryption keys from the content. For example, chunk A and chunk B have identical contents, and the MLE first calculates the cryptographic hash value, for example, SHA hash value of the chunk content, and then utilizes the hash value as the AES key. So after the AES encryption, the ciphertext chunk A and chunk B are identical so that they can be duplicated. However, we observe that even minor modifications to the image content can hinder MLE duplication. For example, the chunk A prime has delta bytes compared to the chunk A. So the SHA hash value is different from the value of chunk A. Therefore, after the AES encryption, the ciphertext A and the A hat are not duplicates, so they cannot be deduplicated. So the state-of-the-art solution is to utilize the locality-sensitive hashing technique in the MLE. It first calculates the superfeature from the chunk content. For example, in case 1, the superfeature in the chunk A and the chunk A prime is identical because the sampled feature F1 and F2 are identical and not affected by the delta bytes. Then it utilizes the content-defined chunking, namely CTC technique, to break up the chunk into variable-sized subchunks to avoid the insertion and deletion and other shift boundary issues. So after the AES encryption, subchunks A1 and A3 can be deduplicated. However, in case 2, the superfeature in the chunk B prime is modified due to the delta bytes. So the chunk B and the chunk B prime generate different keys. Although after the CTC processing, the subchunks B1 and B3 are identical in both chunks, they cannot be encrypted into identical ciphertexts due to the different encryption keys. So unfortunately, they lose the opportunity of deduplication. In our measurements, this false negative rate could achieve up to 49%. Ideally, since chunk B and chunk B prime have a high similarity, they should calculate the same hash value and thus derive the same key, allowing subchunks B1 and B3 to be deduplicated. So this motivates us to exploit the semantic hashing technique to leverage the chunk content semantic to generate the key. So let's go back to the duplication stage. In observation 2, we found that the decompressing Docker image layers before deduplication enhances similarity, decaching, and duplication ratios. However, this process has 2 drawbacks. The first is recompression is needed to restore images to their original forms, increasing pool latency. And the second drawback is that decompressing before deduplication reduces system throughput. So we deeply analyze the decompression process of each layer of the image And we found that it consists of two parts, namely Huffman decoding and LZ77 decoding. This is because in layer compression, the container tool utilizes the deflate algorithm to compress it. The raw data is compressed into the LZ77 stream by LZ77 encoding, and then the stream is encoded by the Huffman encoding into the compressed data as an image layer. To further investigate, we break down the pool latency. As the latency result shows, LZ77 encoding dominates recompression time during the image layer pools. So this raises the question, can Docker images be deduplicated after Huffman decoding instead of completely decompressing, including Huffman decoding and LZ77 decoding? Such a method can enable image restoration only through Huffman encoding, thereby potentially reducing pool latency. So to answer the above question, we partially decode the Docker image using the Huffman decoding, then deduplicate them after dividing them into fixed size chunks. We assess this method's duplication ratio against the complete decompression method, including LZ77 and Huffman decoding. The figure presents here presents two counterintuitive results. The first is the SOTA LSH-based MLE technique for block sketch generation yields a higher duplication ratio in partially decoded space than in completely decompressed space. The second is that MLE, as implemented in AWS Lambda, achieves a duplication ratio over 1 only in completely decompressed space with 4 KB chunking. So to explain the two findings, we conduct a detailed analysis of duplication between two continuous Ubuntu images. The results in figure yield two observations. In the partially decoded space, the layer exhibits more data chunks compared to the decompressed space. The second is after decompression, the layer exhibits the data bloat, resulting in significantly larger duplicates bytes than in the partially decoded space. So this explains the two counterintuitive findings. The LSH-based MLE achieves a higher duplication ratio in the partially decoded space, and the second, the MLE method is more effective in identifying identical parts at smaller chunk generalities, as chunks duplication is not affected by minor modifications. So we summarize our contribution as follows. We explore a new similarity space in Docker images by only using Huffman decoding, which is a new trade-off space of duplication ratio and latency better than the existing completely decompressed space. We propose a fast similarity space selection mechanism that leverages the Huffman tree located at the header of each layer for similarity assessment. And last, we propose a semantic-aware MLE technique, which is the first work to introduce semantic hashing in encrypted decryption for improving the duplication ratio. So we propose SimEnc, and here is the overview. It has two types of clusters. The management cluster maintains distributed metadata and a key database, and rapidly detects the similarity between clients' push layers and existing stored layers. Two storage clusters responsible for storing images and pushing layers to clients. So we have three modes to balance the trade-off between duplication ratio and pool latency. The first mode is the basic duplication mode. It performs layer-level encrypted duplication on the first n layers using the basic MLE. And the remaining layers undergo chunk-level duplication using our semantic-aware MLE after partial decoding. The second mode is the hype duplication mode, which duplicates all layers at the chunk level after partial decoding. And the third mode is the flexible deduplication mode, which utilizes the container images similarity to detect the similarity space for duplication, balancing the duplication ratio and throughput. So in F mode, when the management server receives a new Docker layer, it needs to rapidly determine the duplication space. Our insight is exploiting the Huffman tree similarity of each layer head. as it provides already statistical information about the encoding of compressed content. The results reveal a positive correlation between the deduplication ratio of paired chunks and the cosine similarity of their Huffman tree. However, comparing each layer's Huffman tree in a real-world system poses significant spatial and temporal challenges. To address this challenge, we employ the Bloom filter, a compact bit vector structure representing element sets. If the Bloom filter is hit, the layer needs to be partially decoded and chunk-level deduplication is performed. And otherwise, it is only layer-level deduplication. So the above similarity space selection is the preprocessing of deduplication. We now describe our novel semantic MLE approach for encrypted Docker deduplication. To capture the inherent semantic similarities between Docker layers, we introduce semantic hashing into MLE. At the training stage, we first break layers up into fixed-size chunks, generate the pseudo label by utilizing the X-delta algorithm, and train the hash network to let the output generate similar hash values for similar chunks. We follow the existing works to train the hash network for mapping fixed file blocks into fixed length hash values. However, semantic hashing is not directly applicable in MLE because it produces similar but not identical hash values for similar chunks. So at the inference stage, we propose a similarity-preserving key generation mechanism. It is difficult to generate identical keys for similar chunks. Our key idea is clustering semantic hashes to assign keys to the same class. For example, using the representative chunk key of the class. So we choose the DeepScan clustering algorithm because it forms clusters of attributary strips, doesn't necessarily predefine the cluster numbers. In light of this situation, we ask, is it possible to design an adaptive clustering to set hyperparameters automatically? If we can, the clustering algorithm can be applied to attributary semantic attributes of Docker images, as it automatically can extract suitable parameters from a large amount of data. So we need to automatically stack the clustering distance threshold. Our insight is utilizing the LSH method to guide the measurement of semantic hash code distribution, further to adaptive determine hyperparameters. We observe that over 75% of block sets with the same features are identical. And there is a long tail effect in the CDF distribution. So we set the distance value at the 90th percentile of the CDF, adjusting it adaptively for different images. So we have implemented a prototype of SimEnc in Go and C++. Our code is open sourced. And we deploy the system in 3 PCs and connected with 800 megabits network. And we use 1 GPU for training and inference. We compare SimEnc with 3 baselines. DupHunter is a state-of-the-art Docker registry for plaintext duplication, and AWS Lambda is the SOTA serverless platform for encrypted Docker image duplication using MLE. And the improved AWS Lambda, which deployed the LSH-based MLE. We collected Ubuntu and Couchbase continuous version image from Docker Hub and for the datasets, and used the IBM public workloads. In terms of duplication ratio, SimEnc achieves an average duplication ratio that is 38% higher than the LSH-based MLE and 109 higher on average compared to the MLE implemented in AWS Lambda. Specifically, SimEnc outperforms the LSH-based MLE by up to 54% and MLE by up to 161 in the Ubuntu datasets. We compare SimEnc with DupHunter in terms of duplication ratio and pool latency. In H mode, SimEnc achieves a 45.2% higher duplication ratio and 27.7% lower latency than DupHunter. In F mode, SimEnc improves the duplication ratio by 86.6% 0.2% over DupHunter while maintaining comparable latency. In terms of overall pool latency, we observe that compared to DupHunter, SimEnc achieves an average latency reduction of 72.4% across 4 workloads. This improvement is due to our deduplication in the partially decoded space, while DupHunter performs deduplication in the completely decompressed space, requiring both Huffman and LZ77 recompression processes for restoration. Despite AWS Lambda is a serverless platform, while clients' images don't require recompression after restoration, a fair comparison with SimEnc is possible in terms of the end-to-end latency from requesting to starting the Docker image. We found that in low bandwidth scenarios, for example, less than 400 megabits bps network, SimEnc achieves lower end-to-end latency because it transmits original compressed data. In terms of deduplication throughput, SimEnc provides up to 85% and 75% on average across all workloads of the average throughput compared to the DupHunter. The bottleneck here is the semantic hardship inference time due to we use only one GPU, so we think utilizing multiple GPUs for parallel inference could improve throughputs. So in conclusion, SimEnc is a high-performance similarity-preserving encryption approach for deduplication of encrypted Docker images. We explore a new trade-off space for deduplication by partially decoding, and we propose a faster similarity space selection and the semantic MLE to improve the throughput and the deduplication ratio respectively. Thank you for your attention. That is all from me about SimEnc, and I'm happy to take some questions.